All right, let's introduce the idea of kinetics, the basics of kinetics. Kinetics is the study of how fast reactions go. Most of the reactions that we look at in the laboratory are relatively fast because we want you to get finished within a 3-hour time period, but we do see a wide variety in the speed of reactions, and we also see that we can control it somewhat to a certain degree by looking at several factors. Essentially, when we talk about how fast the reaction is going, we're talking about the rate of the reaction. The rate of the reaction can be thought of as mathematically measuring some change in concentration of some reacting species or some species involved in the reaction over a change in the time. This is kind of like your car traveling down the road is going a certain miles per hour. We're looking at a concentration change. Typically this is in molarity, although it doesn't have to be, versus some time change in the speed of your car. You're looking in hours. Typically in reactions we're looking in seconds. We might be looking in minutes. We could even be looking per hour, just depending on the specific reaction. But in general we see a molarity per second or a molarity per minute or something like that. Let me just remind you that seconds to the -1 is the same thing as 1 over seconds. And one more way that we might see this, a molarity is a moles per liter, so you might see it as a moles per liter per second, or even a mole times liters to the -1, seconds to the -1. I just wrote the same unit 1, 2, 3, 4 different ways. I tend to write it this first way, but you will see it a variety of ways. And again, these are units of rate. How fast is the reaction going? It's the rate, it's the change in concentration over the change in time. There are some factors that affect how fast a reaction goes, and as we develop this material, we'll look at each of these individually, except for the first one. The first factor that affects how fast a reaction goes experimentally is simply the chemical nature of the reacting species. You don't have a whole lot of control over this except for to switch out your reagents, but what we find is that some chemical species react faster than others. The second factor which affects how fast a reaction goes is the reactant concentration. In general, what we find is that as we go to higher reagent concentration, higher reactant concentration, the faster the reaction goes. That's an in general. The third factor which influences how fast a reaction goes is the temperature. Again, in general, what we find is that the higher the temperature is, the faster the reaction goes. The fourth factor we want to look at that affects how fast a reaction goes is the presence of a catalyst. By definition, a catalyst is something that makes the reaction go faster, so the presence of a catalyst makes the reaction go faster. That's what it does, or else we don't call it a catalyst. And then the fifth factor only really shows up when we have solids. If there are solids present, then the amount of surface area does affect the rate of the reaction. If you increase the surface area, you get a faster reaction. All right, as we move through this material, we will come back and visit some of these factors in more detail, but we're still sort of talking about the basics of chemical reactions and chemical kinetics. How fast do reactions go? What ultimately we want to do is we want to develop some equations, some mathematical equations that allow us to calculate things about the kinetics of reactions. So that's sort of what we're building toward. All right, let's look at a specific example of a reaction in order to talk about the rate of a reaction. So I'm going to draw the reaction for the combustion of propane, and then we'll use it as our example to demonstrate the rate of this reaction. All right, there's the balanced reaction for the combustion of propane. It is balanced. Propane is C3H8. The combustion of it means the reaction with oxygen. For the complete combustion, the products are carbon dioxide and water. As this reaction proceeds, we can monitor how fast it goes. In other words, we can look at the rate of that reaction by watching the concentration of one of these things in the reaction. For example, we might watch propane, we might watch the C3H8, And we could say then, or write mathematically, that the rate of this reaction is the change in concentration, I'll use the brackets for concentration, of C3H8 over the change in time. Now the thing about this is since this is a reactant, I start with some initial amount of C3H8, and as the reaction proceeds, its concentration gets smaller and smaller and smaller. That means my change in concentration will be a negative value, and we can't have that. We never write a rate that is negative, and so we put a minus sign out in front. That multiplies by the negative value for the change in concentration, and we end up with a positive numerical value for the rate. You always want a positive numerical value for the rate, so if you write the rate in terms of a reactant concentration, you need a negative sign. If you write the rate in terms of a product concentration, you don't need a negative sign. We'll see an example of that. All right, if I plot the change in concentration versus time, or simply the concentration versus time on a graph, this is my time axis, and this is my concentration. These are the brackets that represent the concentration of C3H8, for example. What I would find is I would start at some high concentration of C3H8. It would drop. It may or may not be linear. Typically it's not very linear, but what I would find after a certain time period is that the concentration leveled off. All right, so that would be a plot of concentration versus time as this reaction proceeds. For kinetics, we are concerned with this graph up into the point where the concentration levels off. Let me make it a little bit later. Here where the concentration levels off, and I am hand drawing this so it's not perfect, where the concentration levels off is essentially when we say, if we're talking about the kinetics, the reaction has stopped. Now what we're going to see as we move on through this semester is it actually hasn't stopped yet. We've reached equilibrium. We've mentioned that word in a couple of videos before, and we're going to talk about this in great detail coming up. But after the concentration levels off, we say that the reaction is at equilibrium, and we're not talking about it in this chapter. We're talking about how fast does the reaction go from here to here. So we're only looking at where this graph is actually still changing as far as the concentration goes. And we can get some details now. Let me make this a little bigger. Alright, I've blown it up, and I know it looks a little weird, but bear with me. On this graph of concentration versus time, the rate is the change in concentration versus the change in time. That's the rise over the run. That's the slope. So the rate of this reaction can be thought of as the slope of this line of concentration versus time. Now the slope of a straight line is easy, but if my line isn't particularly straight, then what is it I'm talking about? And actually, I'm talking about possibly several things. So we have several ways of looking at the rate of the reaction. Often we're interested in the rate at the initial point of the reaction. We'll often refer to this as an initial rate, and that's just taking a very short time period right here at the beginning and calculating the slope of that very short line right at the beginning. We might be instead looking at the rate of the reaction sort of over the whole time period, in which case we would just sort of assume this is somewhat linear. Let's see if I can do this. And I would say, okay, pretend there's a straight line going from here to here. What would be the slope of this line? And that would be the rate of the reaction from this time, didn't mean to move that, from this time period to this time period. Again, a rise over a run, the change in the concentration along the y-axis divided by the change in time on the x-axis. Alternatively, we might look at a rate at a particular time. For example, let's say that for some reason I wanted to know what was the rate halfway through the reaction at this time. I'm not using my straight line, but let me go to it. That would, again, right here is not a particularly straight line, but I could figure the rate by taking a tangent of this point. You may have to review that mathematically. So over a very small portion, pretend like it's a straight line, extend it out both directions, and now I could be talking about the rate at this particular time. So a rate at a particular time, a rate over a short time period or a large time period. what you might see here is I might get slightly different answers for my rate depending on where on this time graph I'm looking at. And that's absolutely true. That's one of the things about talking about the rate of the reaction. In this respect, it might be a little ambiguous, and so you've got to be specific. You've got to indicate clearly where you want to talk about the rate of that reaction. And so you'll see some examples in the textbook looking at different ways to calculate the rate based on this graph. And to make matters even more complicated, if instead of looking at the rate with respect to C3H8, let's say I wanted to look at the rate in terms of the oxygen, or not the oxygen, the CO2's concentration. Let's say I was able to monitor the change in concentration of CO2 with respect to time. All right. In this case, the CO2 concentration is getting bigger and bigger and bigger, so I don't need a negative sign here. But what I would notice on a similar graph for CO2 is that its concentration would start down at 0 because I don't put any initially in, and it would get higher and higher and higher as the reaction proceeded. And then again, at some point it would level off, and so I'd be looking at the rate on a graph that sloped upwards, because now I'm looking at the CO2 concentration. And if I were to calculate the rate at the same time period as this one, here's my CO2, I would not necessarily get the same numerical answer for rate that I got for my C3H8 concentration, because there's some stoichiometry involved. Let's talk about the stoichiometry with respect to looking at the rates of these reactions. All right, bottom line. The C3H8 is going to disappear as the reaction proceeds, as is the oxygen, but they will not disappear at the same rate. I would not calculate the same numerical rate if I was looking at the change in concentration of C3H8 compared to the change in concentration of oxygen. I would still write the equation for both of these with a minus sign, but what I see is that this particular rate is not the same as this rate. This might be a rate 1, this would be a rate 2. Numerically, they're not the same answer because stoichiometrically, oxygen is disappearing much more quickly than C3H8. Same thing if I looked at the rate with respect to CO2 and H2O, I would not see numerically the same values because stoichiometrically, these are appearing at different rates because of the stoichiometry. These are essentially mole-to-mole sorts of conversions if we want to compare the rates of each reactant and product, but there's a shortcut because it is so useful for the rate, in that if I look at the rate of a reaction and I want to write it so that I get numerically the same value no matter which reactant or product I'm looking at, I use the stoichiometric coefficients. So the rate, if I say the rate is equal to the negative change in concentration of C3H8 over the change in time, that will be numerically equal to 1/5 of the rate that I would get for oxygen changing. So 1/5 times the negative change in the concentration of oxygen with respect to time would numerically give me the same value. For CO2, I need 1/3 of the change in concentration of CO2 with respect to time because of the stoichiometry, and then let me try to squeeze it in. For water, numerically this would be equal to 1/4 of the change in concentration of water with respect to time. And I could use this, for example, if I was monitoring the C3H8 concentration change versus time, I could calculate what the CO2 concentration versus time change would be by using this equivalence. For every one of these that disappears, 1/3 of a CO2 appears, and I could solve for the change in concentration of CO2 with respect to time, for example.